Well, hello, ladies and gentlemen. So let's do an example today, our first example involving application of the energy balance to an open system, mass and energy balance. Let's do both. We'll apply it to one of the simplest thermodynamic or thermal devices there is, the throttle valve. What is a throttle valve? Well, a throttle valve is a restrictor that is used for reducing pressure in a flow. So let's look at an example here. Example. Throttle valve. Let's put up a schematic what this throttle valve is and what it does. So we have some sort of a tube right here. Could be a circular tube of some kind. And then we have a restrictor. So the tube all of a sudden reduces diameter. And then we have an increase in area, okay? That's basically what a throttling valve looks like. The left-hand side is the inlet, and the right-hand side is the outlet. So the inlet I'll call location number 1, and the outlet I'll call location number 2. So what we have here is we have steam, or if you like, a mixture of saturated vapor and liquid. So location 1, we have what's called wet steam. In other words, a saturated mix with some quality X1, typically very close to 1. So we got wet steam coming in from the left-hand side of my throttle valve. So the given, we've got a throttle valve. Let me put up the givens and the finds here. So given adiabatic, so I'm going to wrap some insulation around this thing. An adiabatic throttling valve. So it's a restrictor, a pipe with a pinch section or a restrictor, and it's used for dropping pressure and expanding steam in this case. So we got an adiabatic throttle, a throttle or a throttle valve, whatever it is you want to call it, okay? The inlet pressure, P1 is 20 bar. The outlet pressure, P2, is 1 bar. So we got pressurized steam, wet steam with some sort of quality close to 1 coming in, and we got a drop in pressure. So P1 is greater than P2, a drop in pressure, and the steam expands at the outlet, okay? Steam out, wet steam in. The outlet temperature, T2 is 120 degrees C. By the way, the saturation temperature for 1 bar is about 99.9 degrees C. So we're above the saturation temperature, so we get a superheated steam. Superheated steam coming out, okay? Superheated steam. All right, so I got pressures on the inlet and the outlet. I got an outlet temperature. What am I supposed to find? Tell you what, getting a little bit disorganized here. I guess I will put the find and the assumptions over here. Let's find the inlet quality for the saturated H2O mixture, the wet steam. Let's find the quality of the steam called wet steam. It's basically, we're going to find out that it's basically a saturated mixture with a quality very close to 1. It's steam with a few drops here and there of saturated liquid, wet steam. So let's find the inlet quality for the inlet wet steam. And then I'll list in the assumptions as we go along. We might have some assumptions in this problem, all right? Okay, well, let's begin our analysis here. Analysis. By the way, I think I'm going to put, whenever we do this kind of a problem, I think I better put the saturation dome up and indicate state 1 and state 2 so we can figure out what tables to use. Instead of putting temperature and specific volume here, I'm going to do temperature and specific enthalpy. It qualitatively looks the same as temperature versus specific volume, so we're going to have the saturation dome. So here's our saturation dome right here. And then, so here are our isobars. Okay, so there's an isobar right there. So TH instead of TV, just so we can figure out what's going on. Just so we can figure out what's going on. So I want to know what the inlet quality is. Now, if I had an inlet enthalpy or an internal energy, if I had H1, I could get a quality at state 1. Or if I had a U1, if I had a specific internal energy or a specific enthalpy at the inlet, I could get the quality at state 1. Okay? So really, the problem should be driven by trying to find the inlet specific enthalpy, H1, or internal energy, U1. So what equations have H's or U's in them as far as open systems? Oh, let's define our system. Let's define our system here. So this is clearly an open flow device. So here's my system. It envelops the inside of my valve, on the walls of the valve. I don't want it pinching to nothing here. That's not good. There we go. Okay, so the flow is going in and out of this constriction. So that's an open system. I got an inlet at location 1 and an outlet at location 2. So why don't I try applying the mass and energy balance to my throttle. Let's apply the mass balance first. Let's see what the mass balance gives us. Now there's going to be mass flows in my energy equation, so I need to know something about the mass flows. So mass balance, open system. dm/cv dt, that's the time rate of change of mass within my valve, is equal to the sum of the inlet minus the sum of the outlet flows, okay? Now, first of all, how many inlet and outlets do we have? We got one inlet where the wet steam comes in, and we got one outlet where our superheated steam comes out. One inlet, one outlet at location 1 and location 2. So these summations collapse to one term. The m dot is at location 1, and the outlet m dot is at location 2. The inlet location 1, the outlet location 2. Now, what about the time rate of change of energy within my throttle valve? The change in mass, I'm sorry, mass, not energy. The change in mass within my throttle valve over time, my control volume. Well, there's nothing in the problem about time dependence, about the flows in and out changing with time, or about mass building up inside the valve or depleting in the valve. So I'm going to assume steady state flow. So steady state, steady flow. Assumptions, steady state, steady flow. So this is going to apply, well, steady state. Steady state implies dmCV dt is equal to 0. No change in mass within the control volume. So I can set this to 0. Steady state. If I assume steady flow, then these mass flows don't change in time either. So I think I'll write steady flow SF m dot 1, m dot 2 are constant. No change with time, okay? So this says 0 is equal to m dot 1 minus m dot 2, or m dot 1, the inlet flow, equals m dot 2, the outlet flow, and since they're both equal each other and they're the same, I'm just going to call the mass flow rates at the inlet and the outlet m dot. They're both the same. Energy balance says mass balance says if we're in steady state, steady flow, then steady state, then these two mass flows are the same at the inlet and the outlet. So instead of referring to m dot 1 and m dot 2, I'm just going to refer to m dot. I'm going to drop the subscript, okay? So m dot 1 is equal to m dot 2. Inlet and outlet mass flows rates are the same and constant. Let's apply the energy balance now. E balance. Open system. Q dot minus W dot is equal to the time rate of change of energy within my throttle valve, the control volume, plus the sum of m dot H plus PE plus KE summed over all outlets, minus the same thing summed over all inlets. M dot H plus PE plus KE. All right, let's look at our throttle valve and figure out what the heat transfer is. Q dot. Is there any heat transfer into my throttle valve? It says here, it's an adiabatic throttle valve. Adiabatic means no heat transfer. Adiabatic. Q dot equals 0, okay? No heat transfer. It's an insulated, that throttle valve is wrapped up in insulation, so we're going to neglect the heat transfer. 0. Adiabatic. Q dot is gone. What about W dot, the work term? Remember, in the open system energy balance, W dot has 3 components: boundary, shaft, and electric. The pressure power has been absorbed into the enthalpy term. The m dot terms in the form of enthalpy. The U became an H. So let's ask ourselves, is there any kind of work going on here with the exclusion of pressure power or pressure work? We don't have to worry about that. Are there any shafts or wires inside the control volume? Is there a little propeller in here somewhere? It's just a tube with a restriction and then it flares out. That's all it is. It's a tube with a certain diameter, it shrinks, and then it flares out as it expands the steam. So there's no shaft, no wires either. There's no electric work or electric power going on. What about boundary work? That's due to a change in volume of the control volume, the system. Any change in volume is this tube, this throttle valve, twisting and getting distorted over time. I don't think so. I have no indication that the actual throttle valve is changing shape. Therefore, it's not changing volume. Therefore, there is no boundary work. So I'm going to write down here in assumptions, W dot equals 0. No shaft, no electric, no boundary work. Okay, no work. Steady state. That means nothing changes with respect. That means the amount of mass and the amount of energy doesn't change with time in the control volume if we are in steady state. That means dECV dt, the energy within the throttle valve doesn't change with time. So I'm going to write 0, steady state. The amount of energy inside the throttle valve, our control volume, energy within the control volume, the throttle valve, doesn't change in time. Why? Because I'm assuming steady state. So not only is it dmCV dt is 0, but dECV dt is 0. No change with time for energy and mass within the control volume. Steady state. Steady state. What other terms can we look at? What else can we maybe get rid of in this particular, in the energy balance? What about these specific kinetic and potential energy terms at the inlet? Okay, so we need to work on these mass flow terms. Well, let's work on the outlet term. The sum of m dot h plus PE plus KE summed over all outlets. How many outlets do we have? Well, as you can see in the diagram, we have one outlet, and that is at location 2. We also have one inlet. That's at location 1. One inlet, one outlet. So the summations go away, and the outlet term becomes m dot 2 h plus PE plus KE at the outlet. One outlet, and that's at location 2, so m dot h PE KE at 2. At the inlet, we have one inlet, so the summation goes away, and I get m dot 1 h plus PE plus KE at the inlet, which is at location 1. Let's write what I got. Let's write what I got. Remember, m dot in is equal to m dot, I'll leave that right there. So all the mass balance stuff. So let's write what I have. 0 equals m dot 2 h plus PE plus KE at the outlet minus m dot at the inlet, m dot 1 h plus PE plus KE at the inlet. Okay? Whittled away a lot of the energy balance here. A lot of the terms are gone. Let's see if we can get rid of something else. Mass flows. See if we can deal with these. Remember, m dot 1 is equal to m dot 2. So this is just m dot. They're the same. The inlet flow is equal to the outlet flow. If they're the same, they're both m dot, I can divide both sides of the equation by m dot and they go away. So I get 0 equals h plus PE plus KE at the outlet minus h plus PE plus KE at the inlet. Can we get rid of anything else? These kinetic and potential energy terms. The kinetic energy terms at the inlet and the outlet, that's specific kinetic energy. Those have to do with the average flow velocity. So like this guy here, KE at the inlet, this is going to be 1/2 times an average velocity at the inlet squared. So it's going to be 1/2 velocity at the inlet squared. And on the outlet, it's going to be 1/2 velocity at the outlet squared. Now, we're not given any information about the inlet and the outlet velocities. I don't have any flow areas. I don't even have any m-dots. So I cannot calculate any of these inlet and outlet velocities and therefore specific kinetic energy terms. So I'm going to assume them away. I'm going to assume them away. I have no information on the inlet and outlet kinetic energy or velocities of the flow. So I'm going to assume KE1 equal to KE2. I'm going to assume they're the same and let them cancel out in the energy balance, okay? I'm going to assume that we can neglect the contribution of the kinetic energy term, okay? Another way of writing this, maybe a better way of writing this, probably a better way of writing this is delta KE from the inlet to the outlet is 0, okay? That means they're both the same. KE1 is equal to KE2. That's what that delta KE1 to 2 is equal to 0 really means. Okay? So we're going to neglect the contribution of kinetic energy change in the energy balance. Same thing with the change in potential energy. This has its roots in the gravitational potential energy of the flow. It has to do with the height of the inlet and the outlet. I don't see any indication that the inlet is significantly different in position than the outlet. I have no information on the height of the inlet and the outlet. So I'm also going to neglect the change delta PE from the inlet to the outlet. I'm going to neglect that too. I got no information on the position of the inlet and the outlet, so I'm going to neglect these terms. Neglect these terms. All right? So what have I got left? 0 equals H2 minus H1. Or if you like, H out is equal to H in. H out is equal to H in. I'm going to put a nice dash box around this. This is an important result. H out is equal to H in. So the energy balance tells us that the inlet specific enthalpy and the outlet specific enthalpy are the same. H2 is equal to H1, okay? Now remember, if we want to get the inlet quality for the wet steam, I need to know an enthalpy at the inlet. So this really tells me H1 is equal to H2. What's H2? Well, let's see if we can calculate an H2. Let's go back and look at our problem statement. So I know the outlet is at 1 bar and 120 degrees C. It's going to end up being a superheated vapor. So H2 is H, evaluated at P2 is 1 bar, and T2 is 120 degrees C. Let's see if we can look that up. Oh, I'm running out of space. Let's do it over here. Let's go to the superheated vapor tables. Superheated vapor tables. Saturation tables. Superheated vapor tables. 1 bar, 120 degrees, specific volume, internal energy, enthalpy, 2716.6. 2716.6. kilojoules per kilogram degree, I'm sorry, kilojoules per kilogram. I'm sorry, 2716.6 kilojoules per kilogram. Turn the share off. 2716, okay? So state one, I'm sorry, state two, right out here. Sorry. Excuse me. It's all chalk. Sorry about that. We know that P2, I'm sorry, the inlet is at a higher pressure than the outlet. Let me put on the two isobars here. So here's P2, which is a lower pressure. Let me make sure this is right. Temperature. Yeah, should be okay. Okay, so at state two, hold on a second. Let me pause it here for a second. I do want to break this up. Okay, so let's continue on here. One little thing I want to clarify here. I usually don't use the TH diagram, so I think I might have misspoken a little earlier. There is a saturation dome on the TH plot, but it doesn't, it's qualitatively similar, but it's not exactly the same. The TH plot looks kind of like on the saturated liquid side, just like the TV plot, but on the saturated vapor side, it folds over on itself, or it curves over and becomes concave. So it looks something like this. So this part here is a little bit different than the TV plot, okay? Now the isobars look the same. So here's the isobars. So here's our high pressure inlet, P1, and here is our low pressure outlet, P2, okay? So we're at 1 bar, and we're at 20 bar up there, okay? Now P2 is a superheated vapor, so we're like right there. Well, we'll see in a minute. But presumably we're in the superheated vapor region on the P2 isobar. Okay, now the ice enthalpic, H2 is equal to H1, so a new word. Ice enthalpic means that we're moving vertically on the TH plot. We're going from a high pressure to a low pressure on the TH plot, and we're moving vertically up and down. So this is an isenthalpic process. So I'm going to write right here, I'll write it over here somewhere. Isenthalpic, brand new word, isenthalpic. Constant enthalpy. Enthalpy, isenthalpic. Isenthalpic, constant H, constant enthalpy, isenthalpic process, brand new word. Brand new word. Okay, so we have an isenthalpic process going on through the throttle valve, and that means a movement vertically on the TH diagram. Remember, the saturated vapor side of the saturation dome curves in this kind of strange manner compared to the TV and the TU plot. Okay, that's just what enthalpy does, all right? So I guess, strictly speaking, TH and TV aren't exactly qualitatively the same. You got this odd behavior on the superheated vapor side. Okay, so let's calculate the quality at state one. Quality X1 is equal to the quality evaluated for an enthalpy H1 of 16.6 kilojoules per kilogram and a pressure P1. P1 is 20 bar. Okay? Let's check H for a saturated vapor. Let's check H for a saturated vapor at 20 bar. What is the specific enthalpy? Let's see if we are above or below it. Let's see here, pressure table, 20 bar. Specific enthalpy, 2799.5. That's for the saturated vapor at 20 bar, 2799. We are below 2799. So notice this is less than ACE sat vapor, which is 2799 kilojoule per kilogram. So we have a saturated mix at state 1. So this isenthalpic process, so here's state 2, and here's state 1. That's the process, an upward, a downward movement from state 1 to state 2, the isenthalpic process, and it's a saturated mix. Okay, well, that means we need to use the equation for quality. Let's see here, this is going to be equal to H1 minus H sat liquid evaluated at 20 bar divided by H sat vapor minus H sat liquid evaluated at 20 bar. By the way, new nomenclature here. This quantity, H sat vapor minus H sat liquid, this guy, it's used a lot. We use it so much, we created a new quantity, H sat vapor minus H sat liquid, called HFG. The enthalpy change from fluid to gas, HFG. So H1 minus H sat liquid at 20 bar divided by HFG evaluated at 20 bar. HFG is given in saturation tables. Okay, so let's look at the specific enthalpy for a saturated liquid at 20 bar and HFG. Saturated liquid, 908.97. Let's see, so H1 is 2716.6 minus 908 kilojoule per kilogram. H sat liquid, 908 approximately. And then we have HFG, the enthalpy change from fluid to gas, 1890.7. 1890.7. 1890.7 kilojoule per kilogram. Turn this off. HFG, 890.7 kilojoules per kilogram. Kilojoules per kilogram cancel out. And what is our final quality? It looks like it's going to be pretty close to 90-something%. Let's see here. 2716.6 minus 908 divide by 1890.7. 95%. 0.956. Or 95.6%. quality of the inlet wet steam, X1 equals 95.6%. Okay? So the steam comes in almost a saturated vapor. 95.6% of it is saturated vapor by mass. And then it's expanded through the throttle valve to produce a superheated vapor. And remember, the TH diagram has this curve here, okay? Has that curve. So the inlet quality for the steam X1 equals 95%, and pressure P1 is 20 bar. And the outlet T2 is 120 degrees C, and P2 is 1 bar. We dropped the pressure, and we expanded a mixture of saturated liquid and vapor to a superheated vapor, okay? So we learned how to apply the energy balance and mass balance to our first simple open flow device, a throttling valve. There's nothing going on in this valve. No heat transfer, no work. We're neglecting changes in kinetic and potential energy. Therefore, the energy balance tells us it's an isenthalpic, constant enthalpy process. Isenthalpic process. H2 is equal to H1. Inlet enthalpy is equal to outlet enthalpy. And then we established that we started with this superheated, with a saturated mix, and we expanded to a superheated vapor. Okay, I wanted to spend a fair amount of time on your first example today of the energy balance for an open system. We'll move on next time to two more complicated examples involving work-producing or consuming devices, turbine compressor, or nozzles and diffusers, devices which do something a little bit more than this throttling valve. The throttling valve is isenthalpic. Take care, ladies and gentlemen.